So last time I have introduced discrete time Fourier transform, which is defined as x of e to the power j omega is equal to summation of xn into e to the power minus j omega n, n going from minus infinity to plus infinity. We have represented this as a function of omega. Instead of writing it as a function of omega, we have written it as function of e to the power j omega. This is to understand that x e to the power j omega is a periodic function, periodic continuous function of omega. What is the periodicity? Periodicity is 2 pi. It is periodic. Since e to the power j omega is also periodic with period 2 pi, x e to the power j omega is also periodic with reference to 2 pi. The relationship we have seen, this expression we have obtained from continuous Fourier transform, which said x of j omega is equal to integration minus infinity to plus infinity x of t e to the power minus j omega t dt. This is converted to x e to the power j omega. While doing that, we have used a relationship which is omega is equal to capital omega times t, where this t is sampling period. So, when this omega takes up the value, if this omega is 0, this omega is also 0. If this omega is 2 pi, what is this omega? This omega is equal to 2 pi by capital T multiplied by T, that becomes 2 pi. This omega is what? 2 pi by T. What is this 2 pi by? If T is sampling period, what is 2 pi by T? It's omega s, sampling frequency. So 2 pi becomes sampling frequency. Is that clear? 2 pi is equivalent to sampling frequency omega s. So what is pi? Pi will be omega s by 2. What is omega s by 2? The maximum frequency contained in the signal which we started with. We started with sampling. A continuous time signal is sampled at the rate of twice the maximum frequency contained in the signal. What is the maximum frequency contained? It's sampling frequency by 2. That maximum frequency, this becomes B. So pi goes to B. And that is what is the area of our interest. Fourier transform usually is an even function. Magnitude spectrum is an even function from minus omega s by 2 to plus omega s by 2, because that is the frequency range in which we are interested in. Why are we interested in that range? Because we have assumed that our continuous time signal is band limited to B. When it is band limited to B, we are not interested in any other frequencies higher than B. And that is why we sampled it at the rate greater than twice B. Omega s must be greater than twice B. Alright? In general, it is said that no signal in real life is band limited. However, the band limits are defined with a convenience of the user, convenience of the human being. Otherwise, no signal in real life is band limited. The band limits are defined. For example, biomedical signal has a bandwidth of 100 hertz. It is assumed that higher frequencies, even if they are contained, they are not carrying any information contained in the signal. That is why band limit is 100 hertz for the biomedical signal. Audio signal is 20 kilohertz. Lower limit is 20 hertz to 20 kilohertz, and so on. Band limits are defined, but that doesn't mean that the signals are band limited. Alright? That is why pi becomes omega s by 2. So our region of interest Suppose if I draw the spectrum of a discrete time signal from, say, this is minus omega s by 2 to something, I am taking slightly greater. This is our B, this is minus B. So, B is greater than omega s by 2, B is less than omega s by 2. Alright, it can be equal to. Can it be? No, it can't be. It has to be slightly greater than twice B. It cannot be equal to. Alright, we will see that little later. Why it can't be? Because the signal cannot be, in some cases the signal cannot be represented, cannot be recovered from the samples if it is sampled exactly at 2B. Alright, so that means our region of interest is minus omega s by 2 to plus omega s by 2 with reference to omega. When the signal is a continuous is obtained, the discrete time signal is obtained from its continuous time counterpart. If it is naturally discrete time, then our interest is minus pi to plus pi. So the bandwidth of discrete time signal is always 2 pi, and this is actually evident from this Fourier transform, which is discrete time Fourier transform. X e to the power j omega is a continuous function of omega. The function is periodic, this function, that is why only one period is drawn. This is periodic. So the next period comes here. What is this value? This value is omega s. Omega s means 2 pi. 0 to 2 pi or minus pi to plus pi is the region of interest for the discrete time signals or digital signals. So bandwidth of digital signals, bandwidth of discrete time signals is 2 pi. Discrete time or digital signals is always 2 pi. Whether it is sampled by using a kilohertz frequency range or megahertz frequency range or terahertz frequency range, the interest region is minus pi to plus pi. It is constant. But how it is related to? Then it is related to the discrete frequency is related to the digital frequency is related to analog frequency by using this relation. Here the value of t is changing. For a megahertz range, see, this t by t cancels. That is why it is constant. If this t is say sampling frequency used is 1 kilohertz, then what is the value of t? 1 millisecond. This 1 millisecond cancels with this 1 millisecond, constant. When it is 1 megahertz sampling frequency, then the sampling period is 1 microsecond. This 1 microsecond cancels with 1 microsecond. It has no unit, so it is always constant. Discrete time signals has a constant bandwidth which is equal to 2 pi. This is taken from x to x plus 2 pi. X, any value of x to x plus 2 pi. That means one period is 2 pi. So when x is 0, it is 0 to 2 pi. When x is minus pi, it is minus pi to plus pi. Alright? This is what we have seen last time. Let's see one example of obtaining a discrete time Fourier transform. The example is a rectangular pulse. So this is n equal to 0, 1, 2, 3 and 4. So what is this signal? This signal is x of n. Xn is equal to 0, 1, 2, 3, 4. How can you write this signal as? I write this as x of n is equal to u of n minus u of n minus n minus 5. So u of n is this. This is 0, 1, 2, 3, 4, 5 and u of n minus 5 is this. So 5 gets cancelled. So what remains is 0 to 4. So in general, if I write x of n to be equal to u of n minus u of n minus capital N, where the signal x of n will be equal to 1 for n is equal to 0, 1, 2, n minus 1 and is equal to 0 otherwise. The signal can be represented in this form or this form. Here I have chosen n is equal to 5. So I have chosen n is equal to odd. We will have to see Fourier transform when n is odd and when n is even. Alright. This can be written as, so x of e to the power j omega will be equal to summation of xn e to the power minus j omega n, n going from minus infinity to plus infinity, since xn is only 1 in the range of n going from 0 to 4. Xn is 1 multiplied by e to the power minus j omega n. So this is equal to 1 plus e to the power minus j omega plus e to the power minus j 2 omega plus e to the power minus j 3 omega plus e to the power minus j 4 omega. This can be written, now for n equal to 4 I could have written this, but for n equal to 100 I wouldn't have. So in general I can write this as, now it is a geometric series, 1 e to the power minus j omega, e to the power minus j 2 omega and so on is a geometric series. Series in geometric progression, wherein there is always the ratio of the next term to the previous term is always constant. What is that? It is e to the power minus j omega. Alright, and such a summation can be written in closed form as the first term is 1 multiplied by 1 minus common ratio. What is common ratio? It is e to the power minus j omega to the power number of terms present in the summation. How many number of terms are present? 5 divided by 1 minus e to the power minus j omega, common ratio. First term multiplied by 1 minus common ratio to the power number of terms divided by 1 minus common ratio. That is the closed form for any series in geometric progression. I can write the summation in the closed form. You understand this? I rewrite that for you. First term multiplied by 1 minus common ratio to the power number of terms divided by 1 minus common ratio. CR is common ratio, FT is first term. If first term would have been other than 1, then I would have written that here. We will see that little later with some other examples. So this is a generalized formula for what? For closed form summation. For closed form summation of geometric series. Closed form solution for a geometric series. Now come here. So this can be written as 1 minus e to the power minus j 5 omega divided by 1 minus e to the power minus j omega. This is a complex quantity. I want you to find out its magnitude and phase separately. I want you to obtain mod of x e to the power j omega and argument of x e to the power j omega separately. Please do this. So we start with x e to the power j omega is equal to 1 minus e to the power minus j 5 omega divided by 1 minus e to the power minus j omega. Why don't we take e to the power minus j 5 omega by 2 common from the numerator? From the numerator you take e to the power minus j phi omega by 2, and from the denominator you take minus j omega by 2. Half of this. What will happen in the numerator? It becomes e to the power j phi omega by 2 minus e to the power minus j phi omega by 2 divided by e to the power j omega by 2 minus e to the power minus j omega by 2. So this multiplied by this is 1, this multiplied by this is e to the power minus j phi omega. And then you can write, what is this? This is e to the power minus j 2 omega. What is this numerator? Twice j into sine of phi omega by 2 divided by twice j into sine of omega by 2. So twice j cancels. What remains is sine of phi omega by 2 divided by sine of omega by 2 multiplied by e to the power minus j 2 omega. So I can write mod of x e to the power j omega as equal to mod of sine of phi omega by 2 divided by sine of omega by 2. Sine phi omega by 2 by sine omega by 2 is a real quantity, but it may be sometimes positive, sometimes negative. So I have to write mod here as well. So this function resembles magnitude. That is why it is called as pseudo magnitude. So I call this as, and what is the phase? Argument of x is e to the power j omega is minus 2 omega plus something. I will say plus theta 0. We will define what is theta 0. Why this minus 2 omega? It is very clear. This is equal to minus 2 omega. But when this is positive, it is minus 2 omega. When this is negative, it is plus or minus pi. This, the value of theta 0 is, if this value is negative, magnitude cannot be negative, but this value can be negative. So the function, the phase that makes this positive is to be added here, which is either plus pi or minus pi. So I can write, if I write this as m, then what do I write? My phase function phi of x e to the power j omega will be equal to minus 2 omega if m is greater than 0, and is equal to minus 2 omega plus or minus pi if m is less than 0. I will make it clear once again. This we have already done with Fourier transform, magnitude plotting of the continuous Fourier transform. See, how can I write minus 1? Minus 1 is 1 into e to the power j pi. Plus 1 is 1 into e to the power j 0. So any function, if I write, so minus m can be written as m into e to the power j pi, plus m is written as m into e to the power j 0. So if m is greater than 0, the phase is actually whatever is the phase, that phase remains as it is. But if it is m is less than 0, that means m is negative, that times it becomes plus or minus pi. Is that clear? Any question? Not clear? If it is not clear, please raise the question. Unless you raise the question, I will not come to know whether you have understood it or not. Whatever I have said, I can repeat n number of times, but if it is not of any use, you raise the question, so accordingly I can give my answer. Is it clear? this minus 2 omega, when this value is m, if this value is m, so in general the number is m into e to the power j minus j 2 omega. So this x e to the power j omega is m multiplied by e to the power minus j omega. M is real number, positive or negative. So what is the phase of this? It is minus 2 j omega. But when m is positive, it is minus 2 j omega. When m is negative, it is minus 2 omega plus or minus pi. That plus or minus pi comes from that minus 1. To absorb the negativity of m in the phase, we need to add a phase of pi, which I explained here. Minus 1 can be written as 1 into e to the power j pi. If this is understood, this is very clear. If minus 1 into 1, minus 1 can be written as 1 into e to the power j pi, or 1 is written as 1 into e to the power j 0. So minus m means m into e to the power j pi. So if this m is minus, this m can be written as m into e to the power minus j 2 omega plus pi or minus pi. This can be plus or minus. Alright, now let us see how do we plot this. How do we plot sine of phi omega by 2 by sine of omega by 2? Can you plot it? Make a trial. To plot is here I am going to plot mod of x. Here I am going to plot argument of x. Now friends, remember, when you are plotting a discrete time Fourier transform, the range of the plot is minus pi to plus pi only. So let me mark those minus pi to plus pi. Because outside this is going to be periodic. So I am going to mod of x is mod of sine of phi omega by 2 divided by sine of omega by 2. First I want to plot this for various values of omega. Now first, what are the zero locations? Locations of zeros on the magnitude of this function. When will this function become 0? When the numerator becomes 0. When the numerator becomes 0 means sine of phi omega by 2 becomes 0. For what values of omega? For phi omega by 2 is equal to 0, plus minus pi, plus minus 2 pi and so on. Which implies omega is equal to 0, plus minus 2 pi by 5, plus minus 4 pi by 5, plus minus 6 pi by 5 and so on. These are the locations of zeros. These are the values of omega for which the magnitude function is 0. So tell me what are the locations? So first is 0. I will only mark those locations. Alright. Second location is 2 pi by 5. So I will have to make 5 parts out of this. So this is 2 pi by 5. This is 4 pi by 5. 6 pi by 5 is above pi. So we are not interested in that. 6 pi by 5 is above pi. We are not interested in that. So also minus 2 pi by 5 and minus 4 pi by 5. At these locations, the magnitude is 0. Magnitude, there is another location also when the denominator is infinity. When the denominator is infinity, that time also the magnitude is likely to become 0. But any value of omega for which sine omega by 2 is infinity, no question. That is why we have not considered that. Now, we will have to find out this ratio at these values. So first 0 value. When omega equal to 0, what is the value of sine phi omega by 2 by sine of omega by 2? It is 0 by 0. It is 0 by 0. So how will you do? How will you proceed? You can write this as sine of phi omega by 2 divided by sine of omega by 2 multiplied by phi omega by 2 divided by phi omega by 2. And then this is one sinc function and this is another sinc function. So in general this can be written as 5 times sine of phi omega by 2 by phi omega by 2 multiplied by omega by 2 by sine of omega by 2. As you know, at omega equal to 0, this value is 1. So also is this value 1. Sin x by x is 0. So in general at omega equal to 0, the value of sin phi omega by 2 by sin omega by 2 is 5. This is 5. Yeah? You can take that. Then also you will get the same value. As he is saying, limit omega tends to 0 of sine of phi omega by 2 by sine of omega by 2, even if you take with usual methods of limits, you will also get the same value. In fact, whatever I have done here is with reference to that only. This is a ratio of two sinc functions. Sine of phi omega by 2 by sine of omega by 2 is a ratio of two sinc functions. Any questions so far? Now before completing this, I want you to plot on the same curve sine of phi omega by 2 and sine of omega by 2. Draw two curves on the same graph, sine omega by 2 and sine of phi omega by 2. Sine of omega by 2. Sine of omega by 2 completes half cycle between 0 to 2 pi or minus pi to plus pi, it completes half the cycle. So it is completing half the cycle. What will sine complete? Sine will be like this, full cycle. Full cycle of sine is like this. That value expanded is sine of omega by 2. So sine of omega by 2 is this. What is sine of phi omega by 2? Phi omega by 2 completes 5 such cycles in the range of minus pi to plus pi. 5 such cycles. So it means I will have to complete this like this. These are 2 pi by 5, 4 pi by 5, minus 2 pi by 5 and minus 4 pi by 5. So sine. Sine means this is your plus 1. For this curve, this is plus 1. For this curve, this is plus 1. So these both are meeting at this place, so it is minus 1. Magnitudes are to be same. My drawing is not as per the scale, but assume that this is going like this. Okay, all the magnitudes are like this. I can redraw it for proper understanding. This is your sine of phi omega by 2 and this is sine of omega by 2. There was a peculiar reason for drawing this. Once you understand this, the other drawing is easy. See here, in this range 0 to 2 pi by 5, 4 pi by 5 and pi, minus 2 pi by 5, minus 4 pi by 5 and minus pi. Identify the locations of plus and minus. Now in this region 0 to 2 pi by 5, both sine 5 pi by 5 omega by 2 and sine omega by 2 are positive, both positive. In this region both are positive, so ratio will be positive, ratio of the two will be positive. In this region sine of 5 omega by 2 is negative, whereas this is always positive. Sine omega by 2 in the range of 0 to pi is positive. So in this region this is negative, so net result is negative. Once again the net result is positive. Net result is the ratio. Sine 5 omega by 2 by sine omega by 2 is positive here, negative here, positive here. Once again here, what happens? Negative by negative is positive. This is negative. And once again positive here. So positive, negative, positive, positive, negative, positive. That is the way sine of 5 omega by 2 by sine of omega by 2 will behave. Alright. Now I will draw it on the earlier slide. The clear question here? Please raise the hand if you have not understood anything. Raise the question. So this is the region where it is both, the ratio is positive, ratio is negative, ratio is positive, ratio is negative, ratio is positive. We have identified the regions of the omega axis. So these are the only sign changes that are happening. Here it is positive, plus 5. At 2 pi by 5 it is 0. It means it must be descending. Now identify the value here, it's negative. It means it's one completing cycle here, half cycle. So it will be somewhat with reduced magnitude than this. We will find out what is the magnitude at this point. Next will be something like this. This magnitude also we will find out. As you see, I have not drawn the magnitude. I have drawn the m value. Capital M, which is pseudo magnitude. I have drawn the function, graph for the function sine of 5 omega by 2 by sine of omega by 2. If it is magnitude, what would it become? Alright, this will go away. The magnitude function would have looked like only this. This is the magnitude function. Now let's try to find out what is the magnitude at this point. Can anybody tell me? So what is the value here? It's exactly between 2 pi by 5 and 4 pi by 5. So this value is 3 pi by 5. So find out sine of 5 omega by 2 by sine of omega by 2 at omega is equal to 3 pi by 5. Find out through calculator. Minus of 1.36. 1.36? 1.236. So this value is minus 1.236. So this value becomes plus 1.236 maximum magnitude. What is this value? Now find out sine of phi omega by 2 by sine omega by 2 at omega is equal to pi. One. As you can see in this, it is 1 by 1. 1 by 1. So it's plus 1. This value is 1. This value also is going to be 1.236 and this value is going to be 1. So it's a decaying sinc function. Sine of phi omega by 2 by sine of omega by 2 is a decaying sinc function. Alright? Any questions so far? Now very important thing is to plot the phase. I want to plot the phase of phi omega is equal to minus 2 omega. So what is phi omega equal to minus 2 omega? When omega is equal to minus pi, when you put minus pi here, phi omega is equal to minus 2 omega. When omega equal to minus pi, this becomes plus 2 pi. When omega equal to 0, it's 0. When omega equal to plus pi, it is minus 2 pi. So it's a straight line joining these 3 points. So let me draw these 3 points, a line joining these 3 points. Let me also simultaneously mark the points of positive and negative. So this is the phase when capital M is positive. Which are the regions? This is the region in which it is positive. So same phase. This is the region which remains the same. This is the region which remains the same. Here is the region, these two regions wherein I need to add a phase of plus pi, alright, or subtract the phase of plus pi, minus pi, subtract the phase of pi, add or subtract, alright. We already know that phase can take up values only in the range of minus pi to plus pi. Anything going outside this will have to be brought back into the range of minus pi to plus pi, which we called as phase wrapping. We will do that in the next stage, next step. Here first is correction due to the magnitude, the value of pseudo magnitude being negative in the regions. So now this is the region in which it is negative, m is negative is the region. So here what I do? I subtract pi. Why I subtract? Because anyway this region is going above pi, as you see. So I don't need to phase correct afterwards. So I subtract pi from it. Subtraction of pi means what? So what would be this value? This value at minus 4 pi by 5 would be 8 pi by 5. Minus twice omega. Omega is minus 4 pi by 5. So phase value is plus 8 pi by 5. So subtract pi from it. What remains? 3 pi by 5 is remaining. 3 pi by 5 is somewhere here. Now what is this value? This is minus 2 pi by 5. This would have been 4 pi by 5. 4 pi by 5 minus pi is minus pi by 5. So the range is this. Straight line. When you are subtract minus 2 omega minus pi, when you are writing, what is happening to the line? The line is shifted by pi units below. If it is plus pi, it would shift pi units above. You understand? Okay. Next, now here, what is this value? This value is minus 4 pi by 5. This value is minus 8 pi by 5. Now this is here what I have to do? I have to add pi. Here I am subtracting pi, here I am adding pi. Alright? So what happens when I add pi to minus 4 pi by 5? It becomes plus pi by 5. And this minus 8 pi by 5, if I add pi, it becomes minus 3 pi by 5. So it's a straight line like this. This line getting shifted by pi units above. This line getting shifted by pi units below. Now you see it's in the range of minus pi to plus pi. Only the phase correction needs to be applied to these two lines because they have gone above pi and minus pi respectively. So what is this? This phase is 2 pi. What you need to do? Subtract 2 pi from it. For phase correction, phase wrapping, you need to either add 2 pi or subtract 2 pi. For this region, you subtract 2 pi. So 2 pi becomes 0. 2 pi minus 2 pi becomes 0. And 8 pi by 5 minus 2 pi becomes minus 2 pi by 5. Somewhere here. This is minus 2 pi by 5. This is 3 pi by 5. This is minus pi by 5. So this line has come down by 2 pi because I have subtracted 2 pi from it. And subtraction of 2 pi doesn't change the phase values. Subtraction from 2 pi doesn't change the phase values. Similarly, here you add 2 pi. So this is what? Minus 2 pi. Minus 2 pi plus 2 pi will be 0. And minus 8 pi by 5 plus 2 pi will be 2 pi by 5. So these are the set of straight lines. So where is our phase now? Our phase would be this function. This is the phase function. Are you with me? the phase function is always in the range of minus pi to plus pi. Okay? The same problem, attention please, the same problem with the value of n we have chosen earlier, it was odd, now it is even. So what is this value? It is u of n minus u of n minus 6. So n value is 6 now. I want you to plot the magnitude and phase spectra. Alright? If you have understood whatever I have done for n equal to 5, you will be able to do it for n equal to 6. I want you to complete the magnitude and phase plot by hand first, and then by using computer is your next exercise. Is it clear? Computer exercise. Next exercise is computer exercise, which you are going to do yourself on the computer in the lab. How do you determine? You are supposed to write the code for this. Alright, the code is going to be very, very simple. Choose x, x is equal to simple. Before are zeros, afterwards are also zeros. First value is at n equal to 0. Then what? For k is equal to 0, colon, max size small x. What does this do? Size of x will you will get? What is this? It's 1 by 9. 1 row, 9 columns. So x has 1 row, 9 columns. So size will give you 1 by 9. Max of size will give you 9, which is what you wanted. Minus 1, because you want this to be 0. MATLAB treats the array location, first location of array as 1 1 or 1. It's always 1 to 9. But we want it to be 0 to 8. So how do you write it as? 0 to max size minus 1. Then what? This is also to be evaluated. This x e to the power j omega, you want to evaluate for values of omega. So for every omega, you have to evaluate this. So I'll complete this first. Capital X is equal to capital X plus small x of k multiplied by exponential of minus j star omega star k. This is star, that means normal multiplication, dot star minus j omega k. What is this doing? It's summing up. For various values of k, it's summing up. And then this ends. this particular loop has to be completed for various values of omega. So this must be in the external loop for omega is equal to minus pi colon 0.01 or 0.001 colon pi. This is to be completed for various values of omega, and then this ends here. But before ending, since omega is a variable that is real and x has to have an index that is integer, I will define a new variable which is integer, which is say L. L is equal to 0 here, or L is equal to 1 here prior to this, and then at this end L is equal to L plus 1, and this x will be of L is equal to x of L plus this. This loop is to be completed. What is this? This is just summing xn into e to the power minus j omega n. This summation is happening here, but I want it to happen for every value of omega, and omega is real variable, whereas the index of x has to be integer. So I have defined L equal to 1 here starting, and then after everything is evaluated, it means for this particular value of omega this is completed. So I have to increase the value of L. This completes the evaluation of x. This is n going from minus infinity to plus infinity. This is equal to x e to the power j omega. That is completed. Now what? Next is you need to plot. Plot what? Omega versus ABS x, comma omega versus, you complete this, let us say figure 1 and figure 2, complete this, and then say plot omega versus angle of x. This angle x gives us the phase angle. Angle gives us phase angle. Now here you give any value of x, any signal x you give, this program determines Fourier discrete time Fourier transform. Alright, this can be easily seen. I will be talking about more computer experiments in this class because we are now doing a really discrete time signal processing, which can be easily done by a digital computer. Although here omega is continuous, I am choosing omega to be discrete. So I am actually getting a sampled version of x e to the power j omega, but I am going to plot it with as a continuous function. Alright, there is a function called as unwrap or wrap for that matter. These functions evaluate unwrapped phase or wrapped phase. Wrap is not required because it is given by angle. Default phase is always wrapped phase. If you want to unwrap the phase, that means getting it outside minus pi to plus pi, you need to unwrap it to see it is linear phase or not. Alright, that time you need to check for unwrap. Is that clear? Any question here? So computer exercise you are going to complete in the laboratory class, whereas this example you are going to do it by hand at home, and today to be completed before 8. If you have any question regarding that, I am going to answer those questions in the tomorrow's class. Alright? Please be on the toes for solving problems if you want to understand. Any questions so far? The linearity property of transforms we have seen for Fourier transform and Laplace transform. It is the same except that the transform becomes discrete time Fourier transform. Now, this is a generalized operator which is called a Fourier operator. When it is applied on a continuous time function, it becomes CFT. When it is applied on a discrete time function, it becomes DTFT. So, what does this state? Discrete time Fourier transform of a linear combination of sequences is linear combination of discrete time Fourier transforms. For this, it is assumed that discrete time Fourier transform of x1n is x1 e to the power j omega and x2n is x2 e to the power j omega. Shift property or shift in time domain. So, what is Fourier transform of x of n minus n0? Shift in the time domain, x of n minus n0. You understand this operator? It is shifted by n0 units towards right, where I have to write n0 because n0 must be integer. I can only shift by integer number of samples. I cannot shift it by fractional samples. So, what is the Fourier transform of this? It is summation of n going from minus infinity to plus infinity, x of n minus n0 times e to the power minus j omega n, which becomes, when I can substitute n minus n0 as some k, so n becomes n0 plus k. No, I am sorry. I have to write n as k plus n0. So, when I write that, and the limits will be when n is minus infinity to plus infinity, k is also minus infinity to plus infinity. So, summation of k going from minus infinity to plus infinity, x of k e to the power minus j omega k plus n0. So, k multiplied by e to the power minus j omega n0. So, e to the power minus j omega n0 comes out, and what is left out is summation k going from minus infinity to plus infinity, x of k e to the power minus j omega k, which is equal to e to the power minus j omega n0 times x of e to the power j omega. So, if it is a linear shift in the time domain, it is associated with phase change. Magnitude, with reference to magnitude response, there is no change. Magnitude of the shifted sequence and the magnitude of the original sequence remain the same. You understand? Whereas only there is a phase shift. So, time shift is associated with phase shift in the frequency domain. Third is Fourier transform of, I hope when we have defined the discrete time Fourier transform, except for the, all the Dirichlet conditions are still valid. Which are the Dirichlet conditions that can be valid and that cannot be valid with reference to discrete time? The first condition is it must have finite number of maxima and minima. No question about it. Similarly, the second condition is it must have finite number of discontinuities. The function itself is discontinuous. So, these two conditions are invalid. But the third condition is valid. What is the third condition? It must be absolutely integrable. Was the condition for continuous Fourier transform. Now, what will it become here? It must be absolutely summable. The function must be absolutely summable. Is the Dirichlet condition that makes the Fourier transform exist. If for a sequence, if the sum is not finite, if the function is not absolutely summable, then the Fourier transform does not exist. Alright. For example, Fourier transform for unit step sequence will not exist. It will exist only in case of, in the limiting case. Like we have done Fourier transform of a unit step function in continuous Fourier domain does not exist. But in the limiting sense, we have obtained Fourier transform of ut to be 1 by j omega, right? So Fourier transform of, now let's take e to the power minus j omega 0 n is the sequence multiplied by xn. Determine the Fourier transform of this sequence, assuming that xn has a Fourier transform x of e to the power j omega. Assuming this, determine the Fourier transform of x e to the power minus j omega 0 n times xn. What do you mean by multiplication of these two sequences? E to the power minus j omega 0 n is one sequence, xn is another sequence. Multiplication of sequences means they must be of same size, first requirement. And then if they are of the same size, then it is a point-wise multiplication. When n equal to 0 for this, n equal to 0 for this gets multiplied. N equal to 1 for this, n equal to 1 for this. N equal to 2 for this, n equal to 2 for this. Alright? When you talk in terms of MATLAB, the star means matrix multiplication. What is point-wise multiplication? It is dot star. It is dot star. When you want to take multiplication of two sequences, point-wise multiplication, then you must make use of dot star. Dot star is a scalar multiplication in case if one of the sequences is a constant. If both sequences are vectors, then it is point-wise multiplication. So what is the Fourier transform of this? Is equal to summation n going from minus infinity to plus infinity xn multiplied by e to the power minus j omega 0 n, which is the sequence itself, multiplied by e to the power minus j omega n, which is equal to summation xn e to the power minus j omega plus omega 0 n, n going from minus infinity to plus infinity. This is equal to x e to the power j omega plus omega 0. What is this property called as? It's frequency shift or modulation. Frequency shift or modulation. So if this is plus, then what happens? This is minus. So if it is plus, here it will be minus. If it is minus, it will be plus here. Okay? Now we are with a point wherein we can determine Fourier transform of xn multiplied by sine of omega 0 n. And so also cosine of omega 0 n. This will be equal to 1 by 2j in bracket sine of omega 0 n is e to the power plus j omega 0 n. So it is x of e to the power j omega minus omega 0 minus x of e to the power j omega plus omega 0. And that for cos this becomes plus and this will go away. It's very clear, e to the power j omega 0 n plus e to the power minus j omega 0 n divided by 2j is sine and divided by 2 is cos. with a plus sign in between. Xn is equal to a to the power n u of n. What is the condition of existence of Fourier transform here? Absolute value of a is less than 1, then only Fourier transform exists. If absolute value is greater than 1, then it is a divergent sequence. 1, 1.1, square of 1.1 is 1.21, cube of 1.1 is 1.3 and so on. It is a diverging sequence. What is a is 1.1 and n is infinity. What is 1.1 to the power infinity? 1.1 to the power infinity is infinity, whereas 0.99 raised to infinity is 0. That means for this sequence the Fourier transform exists only if mod a is less than 1. I am assuming a to be complex. A can be complex as well. A can be real as well. Whatever be the value of a, real or complex, the magnitude of which must be less than 1 in order for the existence of Fourier transform. So what is this? So Fourier transform x of e to the power j omega will be equal to summation of a to the power n, un is 1. So n becomes from, because of this un, n goes from 0 to infinity. Not 1 to infinity, minus infinity to plus infinity becomes 0 to infinity, e to the power minus j omega n, which is equal to summation of n going from 0 to infinity, a e to the power minus j omega to the power n. This is once again a geometric progression with first term being 1. This can be written in closed form as 1 minus a e to the power minus j omega to the power infinity, because number of terms are infinite, divided by 1 minus a e to the power minus j omega, which is equal to, what is this? A to the power infinity is 0. So it is 1 divided by 1 minus a e to the power minus j omega. So the Fourier transform of a to the power n un is 1 by 1 minus a e to the power minus j omega, provided mod a is less than 1. For mod a greater than 1, the Fourier transform does not exist. Is it clear? Any questions so far? We will stop here.